in the body is going about 3 to 5 times faster than, let's say, the use in closure panels, because closure panels have had adhesives and sealant for some time. The glass and sunroof is about growing about 1 to 3 times faster than the market. So there's a significant growth in the adhesive applications because of quality, safety, and of course performance. So the challenge is to determine, how much material did you put down where? So some of the trends in automotive that are driving the use of adhesives is, first of all, the comfort and convenience in larger vehicles has been used for some time now, especially in Europe. The European companies, auto companies, have been leading in the use of structural adhesives for probably 15 years now. But the Americans are catching up, and now the Japanese have started to put the pedal to the metal, so to speak, and are very aggressively growing their use of adhesives. Another big driver of adhesives is handling and performance. Essentially, what adhesives do is they put a lot more rigidity in the body and the structure, so it handles much better. Or safe, energy absorbing in crash, it's better, and of course fuel economy and emissions, essentially lighter vehicles. Now, the impact as far as weight of the vehicle is concerned, there's some are going up, some are sideways, and some are going down. But as far as what is the impact on the weight of the vehicle, what's it doing to the use of adhesives? It's driving the market. So the key, as I mentioned, is do you have the right adhesive in the right place in the right amount? So this is the trend of utilizing structural adhesives in the industry. Of course, the premium vehicles have been using structural adhesives for some time, but what the industry is realizing is that in the entry and mid-range vehicles, if you use structural adhesives, they have similar ride and handling characteristics as a premium vehicle. So that is driving an acceleration of using structural adhesives in entry-level and mid-range vehicles. Now, this information from General Motors is in the public domain, so we're not sharing anything that isn't out there already. But this slide gives you a feel for the trend of using structural adhesives in various types of vehicles. And you can see right now, as the more premium vehicles, the more adhesives. And some of the recent vehicles have well over 100, in this case 184 meters, linear meters of adhesives. And the cost of the adhesives themselves is significant. So you want to know that you're using just the right amount. And as is typical in manufacturing, product development will specify a specific amount And manufacturing will say if a little bit is good, a lot or more is better, especially when they are thinking in terms of sealant and leakage and so forth. So it was only a couple of years ago that an article was written, and one of the industry executives was saying that if the machine vision people would do a better job in controlling the process, we would sell more adhesives. And to a certain extent, they were right when they said that. And so Coherix, obviously, we're accelerating controlling the process. And we're process control people. So the first thing to control the process is to be able to measure it. And this is a 3D measurement problem. We've spent tens of millions of dollars now developing that capability. And now we are, once we can measure, we continually make enhancements that reduce the cost of the process, of course, improve the quality, and we can shorten the time to bring a new vehicle to market. Okay? That concludes my presentation. You want to turn it over?
Thanks, Dwight. I have this slide still on the screen that you show that the CT6 has 184 meters of adhesives. That's fascinating. I think the BMW 7 Series has even more, maybe 150 or maybe 190. I'm confused, but it was somewhere in this range.
And Jaguar Land Rover has pretty much eliminated welding. They use self-piercing rivets and self-piercing screws to hold the parts together. But there's 132 dispensing stations in one body line. So if you can eliminate welding in an automotive assembly plant, you eliminate a very dirty safety challenge, and that's the direction that structural adhesives are driving.
Right. Thanks, Dwight, for the presentation. And I have, a few questions that I have, but we'll take the questions after we are finished with the presentations. And I just want to say to the people online that if you have questions, there's a text box that you can click to, and you can submit your questions there, and we will ask that after all the presentations. So with that, I would turn it over to Christian. Can you hear me?
Yes, Christian.
Okay, I am making you the presenter so that you can share your screen.
Okay. So thank you very much for the very nice introduction. My name is Christian Eholzer. I'm group leader for Sica Corporation in R&D and for body shop adhesives. Can you see my presentation?
Yes, we can now.
Perfect. Excellent. Okay. So Sica Automotive is a leading innovator and supplier for automotive solutions in bonding, sealing, damping, and reinforcing, not only for the car body, but also for the interior and exterior components. And a few examples are structural inserts, acoustic systems, glass bonding, and assembly line adhesives, and of course also body shop adhesives. And this presentation here is in the first part, or mainly about latest trends and innovations in body shop adhesives. So Sica has a long experience with body shop adhesives. The first generation, the first product was in 1988, and at that time, the structural and semi-crash bonding was initiated, and these materials were still relatively brittle. And around 2000, there was a new chemistry, a new technology implemented, and with this new chemistry and technology, we were able to greatly enhance storage stability, corrosion resistance, bonding on aluminum, and also glass beads for hem flange bonding was implemented. Since roughly 10 years, we're now having the third generation, and this is where we were developing more cold pumpable materials, and most importantly, the mixed bonding materials. And the question is now that, as we heard in the presentation before, joining has become more and more important, and probably is one of the most important joining techniques in the body shop. The question is, where does this go, and what's going to be the properties that are going to be relevant for future materials? So today's adhesives come with a set of requirements. One very important aspect certainly is the viscosity of the material, the rheology. Today's materials come with lower viscosity, especially compared to conventional materials in Europe before, which were always used with, or very often used with heated pumping systems. Today's materials are able to be pumped at ambient conditions, and this greatly reduces the application pressures, increases surface life of components or gaskets, can lead to better wettability of oily surfaces, and also cleaning of surfaces of exceeded material becomes less challenging. And this low viscosity in general leads to improved process stability. It's not so difficult to actually reduce the viscosity, but the main challenge is not to lose wash-off performance. Today's adhesives, they can actually do both. They can be very low viscous and at the same time show excellent wash-off resistance. And you can see this on the picture on the right side, where you have two beads of adhesives. One is a high viscous material and one is a lower viscous material. They get spinned in that water bath, and obviously these beads should not be deformed or even washed off. And as you can see, these pictures are after the test, so they're very stable. They show very, very good performance in that aspect. So one aspect of today's and also future adhesives will certainly be low viscosity. Another very important aspect will be new substrates. And here we have an example of two different substrates that we developed solutions for quite recently. On the left side, you can see zinc magnesium, which is a material that shows very, very good tribological properties, meaning it can be very nicely shaped, formed in the stamping process without wearing out too much the tools. And this obviously is a great cost-saving potential for OEMs. However, this coating can lead to adhesive failure at elevated temperatures, and for this specific material, we had to develop a new material in order to make adhesion work again and see cohesive failure in these test specimens. On the other side, on the right side, you can see an aluminum silicon coated boron steel. This coating actually has a little bit a weak connection to the steel, and therefore with a very strong structural adhesive, you can delaminate that coating, and therefore you need to have a more flexibilized system, as shown here on the right side of the picture, with that Sica Power 533 MBX material, which greatly reduces the peak load that exists in this test, and therefore the material breaks cohesively rather than actually peeling off the coating. So these are examples for new substrates that were introduced in the markets and that actually needed new joining technologies or new bonding technologies, new bonding concepts to come over the challenges that were there at the beginning. So this is another important aspect, new substrates. Then always with new substrates, obviously durability and corrosion resistance is important. So also here we see improvements with new products over initial testing with standard adhesives. This is just a general property of next generation materials that for these new substrates, typically we have to pass obviously corrosion tests, but then also very specific tests like cyclic corrosion tests under static load or others. So in this regard, we will see more products or materials being developed, and that's certainly a quite like short-term time scale there. But probably the major driver in the automotive industry since a couple of years and also in the next coming years is obviously lightweighting. And there are a lot of different concepts and strategies that OEMs follow. It's not only the multi-material design that we very often see as an example here, for instance, with the BMW 7 Series. It can be quite a range. There is quite a range of different strategies. We can also have lightweighting with just steel solutions, but then also using high strength or advanced high strength steels. We can have aluminum steel mix, and that was mentioned before. There is also full aluminum solutions like JLR has shown in the past. All these different paths and strategies are feasible. Some come with more potential for weight savings. Some others come with less costs. But all these are possible. But as soon as you start to bond multiple types of materials, multiple or different types of substrates, there you need to have new solutions for joining. And the adhesive systems are certainly the way to go, because conventional mechanical joining technologies or thermal joining technologies as welding will not be flexible enough to actually allow the joining of these different materials. And in Sica, we developed two new technologies. One is the MBX technology, which is mixed bonding excellence, and the other technology is ultra high modulus technology that's coming from one or two components called curing polyurethanes. And both of these technologies aim in combining highly flexibilized or high flexibility with high strength. And why this is important shows this slide here. When we consider a part that is bonded together on one end, consisting of a metal piece and a CFRP piece, for instance, when this is cured in the E-coat oven, the metal is already expanded, and after the oven, the metal tends or will shrink back to its original dimensions, and actually creating stress on the bond line. And if you have a very, very stiff material, then this leads to failure or freeze in of stress and then deform panels. So one solution, or the solution in terms of joining, will be to use a more flexible system, and that's what we propose with the MBX materials. The second aspect of multi-material bonding is to use thicker bond lines. In this example at the bottom of the screen, you can see how this affects the strain. So with increasing bond line, you actually reduce the strain, and this obviously makes it easier for the adhesives to absorb the rest of the strain that is in there. So these two things are important: flexibility of the material, and then also reduction of strain with increasing bond line thicknesses. And how this works in reality shows this slide here. On the left side, you can see a aluminum frame which is bonded to a CFRP sheet, And if you're using a conventional structural adhesive, the CFRP panels starts to deform. That can be observed with a 3D laser profile scan. And you can see that in this example here, we had a deformation of 1.5 millimeters at the center of the CFRP panel. If you're bonding this this component with an MBX material, with a more flexibilized material, the adhesive can absorb way more of the strains, and only a deformation of 0.5 millimeters resulted after the cure. Another example would be the T-pills here of bimetal assemblies. So these are steel aluminum parts or T-pill samples bonded with different types of adhesive, and you can see also here with the use of a structural adhesive and a thin layer, you have quite a high amount of stress leading to deformation of the sample. And if you're using a MBX adhesive at a thicker bond line, the deformation is greatly reduced. So you have less frozen in stress when you use dissimilar materials with an MBX material. So the next generation MBX material will certainly continue to be way more, let's say, tough compared to the initial materials. On the left side here on this slide, you see that with every generation that was actually developed, the impact peel resistance, which is a measure for toughness and crash resistance, if you want, was improved, was increased. And while with the latest generations, we came very close also with the low temperature values to the room temperature values. So that difference between the two test temperatures became smaller and smaller. But with the next generation materials, there will be even a higher increase in the toughness, and that's certainly very, very important also for these type of adhesives. Another aspect is that temperature shielding in the design of the cars can occur, especially when you are having like large parts, for instance, let's say shock towers or other parts where you use thick substrates, and in these situations your adhesive might not see the full temperature of the E-coat oven, and in this situation your adhesive needs to be cured still at the same let's say to the same cross-link density, and therefore you need to have a more reactive curing profile of these adhesives. So the extension of the bake curing window to lower times and lower temperatures is certainly an aspect, especially also for these materials here. So summarizing this presentation, we have seen a quite nice and strong development of adhesive systems over the last, let's say, 10 years. And certain OEMs have actually started to use these modern type of adhesives. As for instance, we have seen with the BMW 7 Series. So the German OEMs are certainly very close in this development, closely followed also by the US OEMs. We see that the Asian OEMs are maybe in this regard a little bit behind, but this has to do probably also with the strategy that the different OEMs are actually following. As I mentioned before, there is different approaches for lightweight design, and just the technology itself does not give you a feedback on how much adhesive is used. But certainly what we see is the latest generations are currently being implemented, and this is where it also will continue with the next generations. New substrates, lower viscosity materials, and multi-material bonding. That's certainly going to be the next steps in this development here. With this, I would like to thank you for your attention and give back to Shashank.
Thanks, Christian. Excellent presentation. Just one question that I was thinking when seeing your presentation: how important is surface preparation for the Sica's adhesives? Do they stick to oily surfaces, or you have special adhesives for those kinds of application, or is surface preparation always necessary?
We have no surface preparation with body shop adhesives. So basically, the body shop adhesives have to stick to the oily panels as they are being used with the OEMs. So there is no cleaning step involved or grinding step involved or something like that. The adhesives are developed to actually bond the surfaces as they come from the stamping plant.
Okay.
But of course, if you have a new type of substrate, you have to check if the adhesion is still sufficient with current systems. So yeah, that's what obviously new types of substrates need that investigation on if it's still working with the current technology, or if you have to change the chemistry a little bit in order to make the adhesion work.
Okay, thank you. Before moving to more questions, I would just like to know if John Carlson is online. John, are you with us? Maybe not. Okay, then let's move to our question and answer session. And I have a few questions prepared. There are also some from the audience. The first is regarding the non-destructive testing. And when we visited your facility, you explained Coherent's technology for doing non-destructive testing for adhesives. Can you explain us a little bit about what that technology is, and then how important is NDT for adhesive applications?
Sure. The objective is to make sure you can control the process so that you know how much adhesive has been put down where. And you need to do this in real time. You got to stay up to the cycle time of the manufacturing process. So we put a three-dimensional sensor around the nozzle. And so you're looking right at the end of the nozzle as the material is coming out. And actually, we have 4 3D sensors, so we have a full 360-degree coverage around the nozzle. And we process 4,000 3D images a second. And everything is right out there at the end of the robot or the pedestal. And the objective is to detect any occurrence where the right amount of material, the volume, is not correct. And that could happen by changes in temperature, changes in speed of the robot. Sometimes if there's a bubble in the lines, you'll have a skip, and in many situations a skip will cause a leak. So you're looking continuously at the bead and making sure that the right volume is putting down in real time.
So you can do this at line speed, right?
That's correct.
Interesting.
It's a very, very challenging 3D machine vision problem to solve. And we introduced the product about 2 years ago. We have 500 or 600 installed at this point in time. And it's accelerating all over the world. We have wholly owned subsidiaries in China, Singapore, Europe, and a distribution partnership with Marubeni in Japan. So we're able to cover the global footprint of these major manufacturers.
Interesting. And there's a burning question around cycle time for adhesive, curing of adhesives. Now, for now, most of the automakers, they have to use fasteners with adhesives just because the adhesive will not cure at line speed, and you have to hold the parts together till it cures, and then the adhesive will take most of the loads, and the fastener is just there for safety. So my question is for Christian specifically, but Dwight, feel free to jump in. What are the new, technologies coming up to reduce the cycle times for adhesives, and where's the market going?
Well, the cycle time for the adhesive, for the bake itself is basically defined by the time that the car body is in the e-coat oven and the following oven. So the amount of energy we have to cure the material, that's what actually defines how the curing system has to be of the adhesive. From that perspective, obviously the OEMs would like to reduce the temperature of the e-coat ovens. That's also an energy question, right? But then there as well, that needs to go hand in hand also with the performance of the e-coat. So the e-coat as well has to cure in that process. So this is basically this all needs to work together. And there is certainly intentions of the OEMs to go to lower temperatures for the e-coat ovens. But what we see right now, it seems more like, for the adhesives at least at the moment, it seems like temperature shielding is the bigger driver for lower curing properties at the moment than really low temperatures at the e-coat oven. And we'll see how this evolves and how this really develops. But at this point, I would say,
as you know, the eco process is right at the end of the automotive process. We're putting in more product into the first tier body subassembler manufacturers because of the outsourcing of a lot of these subassemblies. Now, those parts go from the first tier supplier over to the assembly plant where they're assembled into a body, and that's before they go into paint. So this is where excess adhesive is a problem. If you have squeeze out, this material is not very nice to work with. You get it on your clothes, you throw your clothes away. So it's very important that we get the right amount and we don't get too much, because if it squeezes out, it's a real problem. So people need to know that we're talking days before it gets to the paint ovens.
Dwight, this is Brett, and maybe I've actually written down something that follows up nicely to what you just said. And Christian, you can help here too. But you showed that ATS, I think it was the ATS, the previous generation, the current generation, and there were so many more linear feet of adhesives, Dwight. That means there's a lot more opportunity for overrun and for all kinds of things. What are the significant advancements in application now that are allowing both faster rates, but also far more accurate flow and controlling of the materials? And so you're applying the right amount in the right spots, and then a follow-up to that is, are all of those materials that you showed the linear feet growth, are they the same material, or are you seeing a lot more different materials, and does that affect that technology?
The first part, let me answer the first part. Christian can answer the second part. Once we can measure, once we can see what's going on in the process, then we can optimize it. And there's a number of variables that have to be optimized. It's unfortunate John Carlson wasn't on today because Nordson is one of the large dispensing equipment makers. And we have integrated our product called the Predator in their new dispensing system. And the controls between the measurement, the 3D vision system, and the dispenser are critical. And there's a number of variables. As example, the robot programmer that programs the robot. First of all, the world is very scarce in experienced robot programmers, and they're never where you need them. They're in the other plant. And the problem is you get an inexperienced robot programmer to put down a bad bead real fast. And then you start looking at it and you have to start optimizing it. So there's a number of variables like speed of the robot is a variable, temperature, viscosity of the material. So there's a number of variables that need to be controlled, and that starts with the ability to see it, measure it, and then we can start controlling it, like automatic detection of robot speed changes, very important. The ability to automatically repair a part. When the part is in line, and if you have a defect and you have to take it out, hand repair it, put it back, it's a real problem. So we've implemented the capability to do automatic repair in station. And then you start working on, we all know in sheet metal, there's a tremendous amount of variation. And if the robot programmer programs to a CAD model and has the nozzle of the dispensing unit a certain distance from where the part is supposed to be. And many times with the variation in the sheet metal, the nozzle is dragging on the part. Other times it's too far away and it's what they call snaking. So in order to get a good quality bead, you have to be able to continually measure what is the Z distance between the nozzle and the part and send offsets to the robot, so you're always keeping the nozzle at the right distance from the part. And we've implemented that. It's very, very challenging to be able to do that. You're inspecting in back of the nozzle, and then you're doing Z tracking in front of the nozzle. So we've been working on that especially with Toyota for some time, and it's we're implementing it. So bottom line, there's a lot of variables.
Mm-hmm. And Christian, your thoughts on the different materials? I'm sorry, Sean.
So yeah, as I pointed out at the beginning of the presentation, I think if you're working with low viscous materials, obviously all these challenges become a little bit easier to handle because they become easier to be applied. You don't need that high temperatures to really get the materials to the substrate, to really pump them and apply them. Your bead dimensions are easier to control. As was just mentioned, there is a lot of parameters that need to be really followed closely and optimized in order to make sure that you're always ending up with the right dimension of your bead. And that's certainly true. If your bead size is too large, you have excessive squeeze out, and this is not how we want to apply the material. In terms of length, I think that's two different things. I think in general we apply more adhesive because we see that there's benefits in using the adhesive, as was pointed out, right? So you have more stiffness, better NVH performance. That's true for the structural adhesive, but then you can also make use of crash toughening and better safety, and with this, your variety in type of adhesives increases, and then with the third generation, as I mentioned before, you have multi-material bonding adhesives. So yeah, we see a lot more different types of adhesives being utilized by the OEMs.
One of the concerns from the OEMs is repair from the in-use repair of the body, which is like bonded by adhesives, and the local body shops don't always have the facility to they can weld, but how do they get the adhesive and actually repair the car? So is the industry working to somehow help the local body shops and repair the vehicles? Now I know BMW have to train their dealerships, and there are only few dealerships that can repair their vehicles, especially the I-Series, and they have to send those vehicles to those particular dealerships. So how is the industry tackling that issue?
It's a very good question, and that's definitely very important. We have to provide a repair solution, otherwise we cannot use this technology. So we have a repair adhesive, which is a two-component material. It's not a one-component heat-cured, as all the adhesive that I showed before. That's a two-component, because obviously these repair shops don't have the capability to run the car through an eco oven or something like that. So they need to have a system that is that cures at room temperature. And with the two-component repair solution that we have, there is technology available that repairs can be done. And the nice thing about this product is that it actually comes with a very, very high toughness value as well. So it's very comparable to crash materials that are used in the body shop. It also has 30 newtons per millimeter impact field resistance, which is quite unique on the market. But that's right. That's a very important aspect. And without that repair solution, it would be not that of a universal technology to be used by OEMs.
And you may have read the news that the American Chemistry Council, they partnered with I think it was Western Michigan University, and they created a reversible adhesive which you can actually bond and then debond by the application of heat. So they have nanoparticles in the adhesives, and when you heat it, they vibrate, and because of that energy, it debonds, and then you can rebond. And the fascinating thing is that after you rebond it, the performance actually improves of that adhesive. So it's really fascinating to see that technology. And I talked to ACC, and they said that they are talking with a few companies to commercialize that particular adhesive. And I think that would be really, really good for repair purposes.
Yeah, that's certainly. We're also looking into completely different concepts of adhesives that cure in a different way as today's materials. Obviously, I cannot go into details about what this exactly is, but yes, of course, we're thinking about other concepts than just conventional E-coat curing to get the final performance of the material. And like one of these approaches already actually found its application in reality. That's the ultra high modulus adhesive. That's not a E-coat body shop in body shop adhesive, but an adhesive that is used in the assembly line. And that's a different concept compared to the traditional body shop. This is the cold body shop, right?
Thanks. I'm wondering that you have this vision technology, so I don't think it depends on the type of adhesive, right? It is adhesive dependent, or it can detect any type of adhesive?
This is Michael Tincher. Dwight had to step out of the room just a minute ago for just a minute.
Okay, that's fine.
The answer to your question, though, as an engineer at Coherix, is it does not depend on the adhesive thing per se. Things that do start mattering is we use lasers to inspect the bead, and transparent beads, translucent beads, these start to pose challenges as the laser stops reflecting off of the top of the bead and starts reflecting off of some inner layer of the bead. So when you begin looking at the different, like I said, translucent, transparent beads, that there are additional challenges. Still, the information can be sucked out of the signal, and volumes can be reported.
Okay. Yeah, that's what I was wondering. Like if it's if the bead is transparent, then the light will just pass right through it.
Yeah.
Yeah.
So, certain vision systems, and maybe that's not the same type, but certain vision systems also work on contrasts between colors, and then that has in the past created some requests from OEMs to actually to change colors of the adhesives, but that might be specific to certain types of vision systems.
Okay.
You are. I wanted just to say that Christian is absolutely correct there, and that can be the difference between the 2D systems and the 3D systems, in which, depending on the color, black on black is difficult for a 2D system to see, whereas a 3D system actually sees the bead above the surface. So there are some of the differences that Christian might be talking about.
Okay. Brett, do you have anything to add?
Actually, had a question for Dwight, and maybe you can take it. But Dwight has done a lot of work over the years on competitiveness and international competitiveness. Christian, you pointed in your slides to probably a little bit more activity in this area in the Europeans. Maybe that's due to the European luxury products. But for both of you, and maybe if Dwight steps back in, what are the balance of technology power here in terms of the different continent strengths? I know it's a global market, but what are some of the things that are setting competitors apart, or maybe regions apart, in terms of technology development?
So, yeah, one aspect is certainly that I feel it's somehow a process to go from, let's say, more mechanical joining to adhesives, and then from adhesives, like from structural adhesives, then to crash adhesives, and then from there to multi-material joining. It's not necessarily required to go this way, but it seems like OEMs are, for the most part, first gaining experience with a new technology because they really start to use it in a large amount, right? So first, you start to test your new technology in a small scale before you start to implement it in a larger environment. And I think just traditionally, the Europeans probably have a little bit more experience with using more modern type of adhesives, closely followed by the US as well. But there is also a huge difference between the OEMs on in a specific continent, and that's why these like circles that I drew were quite wide.
Yeah.
So it's maybe not even so a difference between the continents alone, but also between the OEMs that actually differentiates them.
Is it as much a differentiation between market segment of vehicle as region? I mean, luxury cars from Japan to North America to Europe all use a lot because that's kind of the standard, while smaller cars don't because it's cost challenged. So instead of being a regional thing or an OEM thing, it's almost a product segment thing.
Yeah, certainly the product segment is certainly relevant for that, right? As I said, you start to use these concepts on a higher segment model where you have a probably better acceptance for the cost that is involved with that new concept, and then you also have a lower series, less cars that actually are being prepared or built with this new concept. So that's an ideal platform. So certainly that's a correct statement in my opinion. That once you start to use these type of technologies, that's in the higher segment luxury classes first, and then it goes a little bit down. And then obviously it depends on the strategy of the OEM itself, right? So some OEMs are more used to using adhesives and they have crash stuff and adhesives implemented since a while, and then others they're depending still more on structural adhesives and design their cars a little bit different. So maybe that's more than the OEM to OEM difference and the regional differences.
And for luxury market, the performance is important, and adhesives actually adds performance, improves the torsional rigidity of the entire vehicle. So that way improves handling and other things. We have few minutes on the clock, so any closing thoughts, Dwight and Kristen? And if you have questions for each other, you can ask that as well.
Okay. All right.
Okay. Dwight, are you online?
No.
Michael Tincher is still here for Dwight.
Hey, Michael, do you want to have any closing thoughts?
Not this time. I'm an engineer. I was sitting here to help Dwight with any engineering questions.
Okay, Kristen?
So yeah, I mean, I think that statement was made before, and I think that's certainly right. I think OEMs today, they say that they need to use the right material at the right place. That's true for their materials that they're using, and it's certainly also true for the adhesives and the type of adhesives, even for joining technologies. As you heard today, bonding is not the only joining technology. So there is other joining technologies that make sense in specific types of applications. However, I think we have seen that the future of joining certainly is looking very positive for bonding, and especially when it comes down to multi-material bonding or multi-material joining, then it becomes clear that joining has a lot of potential for the future, and from that perspective, that's a very good prospect.
Okay. Thank you so much for presentation, and for people who are on the line, thank you for your time. We were recording this webinar, so we will be sending out a link to everybody so that if you want to refer it at a later time, you can. And we will also write a feature story on this webinar, and we'll put it on our website. So look forward to those emails. Thank you, and have a nice day.
Thank you very much.